Hello everybody, my name is Constantine Victoria, and welcome to Fractional Calculus, the calculus between natural numbers. The name may seem intimidating to the uninitiated, but worry not. Fractional calculus is about exactly what it is called, calculus from the fractional order. So think of derivation and integration from a fractional order. Instead of deriving from the first order, think of what it means to derive from an order between 0 and 1, perhaps from the half order. Doing so may be hard to imagine, but our main concern in this paper is the definition of a more general form of calculus, one that allows us to define derivation and integration from the order of any real number. In a sense, doing this allows us to get a more complete picture of calculus, even though imagining that picture is quite naturally hard, as we will have to interface with more and more abstract mathematical notions. So think not of what it looks like for now, just take its definition as is. Let's start with the historical context. We know that Gottfried Wilhelm Leibniz is responsible for the notation that we widely use today in calculus, the Leibniz notation. While we still use Newton's Fluxion notation, mainly in physics, Leibniz's notation has been the more popular out of the two in modern mathematics. Mathematical notations arguably play an important role in mathematics, as it is the way we quite literally interface with it. So whenever one makes an inquiry regarding our field's notation, it can lead to deeper inquiries regarding the mathematics of the field itself. For example, during his correspondence with Leibniz, L'Hopital wondered what happens when we take Leibniz notation, where n is the element of the set of natural numbers, is generalized to n being an element of the set of rational numbers, namely when n equals 1/2. In a sense, the motivation behind his question was simply a curiosity of what if, rather than a how to. In his reply, Leibniz insisted that such an extension would lead to a paradox, with its resolution possibly yielding far-reaching implications. Unbeknownst to L'Hopital and Leibniz, such a deceivingly trivial question led to the birth of the field of fractional calculus and a trail of inquiries spanning multiple centuries. L'Hopital's question would inevitably be answered in 1816 by S.F. Lacroix in his text An Elementary Treatise on Differential and Integral Calculus, where he briefly mentions a solution to L'Hopital's question, which he arrives at through the generalization of the power rule. So if we take a look at how he approaches it, you can see that he starts with the power rule, and then he continually generalizes it. So as you can see, the generalization of the power rule, where n is an element of the natural numbers, to generalize it further, we will convert this term to this term, which is using the factorial. Now, if you want to generalize it further, where n is an element of the set of rational numbers or the set of real numbers, we'll have to use a special mathematical construction called the gamma function. This allows us to do factorials of non-integer numbers, and that is the secret sauce to this. It essentially allows us to differentiate in the order of real numbers thanks to the gamma function. And in the special case that he covers in his book, where we're differentiating in the order of 1/2, he comes out with this following analytical solution. The gamma function plays a significant role in fractional calculus, as it is one of the primary components through which we can generalize derivation and integration to the rational order and above. In 1823, Niels Henrik Abel introduced fractional calculus to the world in his early papers, including many of the crucial components of the field. He also applied fractional calculus to solve the Tautochron problem, a physics problem in which a frictionless curve is defined such that a bead along its curve will reach the bottom of it at the same time, regardless of its position along the curve. His ingenious, elegant solution motivated Joseph Louisville to derive his own definition of fractional derivation. Now, I won't go through the process as it's quite a mouthful. I've attached my paper below the description if you want to take a look at it, but this is what he comes up with. Notably, there are disadvantages to using his definition, mainly that it works if and only if the series converges. These problems were largely resolved, however, during Riemann's investigation into and continuation of Louisville's work. Of course, not without trouble, as Louisville's definition indubitably led to indeterminate forms in Riemann's initial definition. Before we continue on to Riemann's part, for the sake of simplicity, we will be restricting the domain of order to that of R. That way we can limit the scope of this paper while simultaneously making it more digestible. We can certainly investigate complex orders, however, the scope of that investigation will require tools we have yet to go over, so I will not be covering it. We will also need to extend Euler's differentiation operator to a more general form, one that can work with integration. So instead of this, we're going to use this. As you can see, there's a C, which looks like that C in the integral that we're familiar with, because that's exactly what it is. It's a limit of integration from C to X. With the aforementioned restriction imposed, we can commit to the following set of rules. One roughly states that the operator yields a real solution that is a function of v and x. 2 states that the operator derives when v is positive. 3 states that it integrates when v is negative. 4 states that it returns the original function when v is 0. The previous 3 rules, in essence, generalizes the operator. So now the operator can do both differentiation and integration. 5 and 6 defines the operator's linearity and its resulting product rule. So as you can see, this is like using the same rules of normal algebra that we know, or field algebra. Riemann arrived at a definition for integration that we now call Riemann-Liouville integral, though it is important to note that it does not work for constant functions, unfortunately. Nevertheless, we arrive at the following general definition for the operator and an extension, calculus. Presently, there is a number of definitions for both the differentiation and integration operators, most notably Michel Caputo's differential and integration operators. Note that Riemann-Liouville's definition comes with certain limitation, which Caputo's definition effectively resolves, most notably its requirement for the initial conditions to be defined. Caputo's definition looks like this, where C is a non-consequential term denoting which fractional derivative definition we are using, in which case C equals Caputo. Okay, so let's get into the meat and potatoes. This is going to be a mouthful, so bear with me here. We are going to be solving a fractional order differential equation. So let's start with this equation. Before we move on to solving the equation, however, I'll have to introduce you to Mittag-Leffler's function, which in essence is a power series solution that can yield a known function like arctan x through derivation or integration. For now, don't think too much of how it is derived. Instead, think of it as an initial assumption we have to make. You will see that this construction will be a useful substitution down the line, and don't let that steer you away from its derivation. This function applies to multiple fields of mathematics. I highly encourage you to seek its derivation. I will not cover it in this video, however, for the sake of maintaining the video's focus. So let's switch to Euler's notation. So instead of using Leibniz's notation, we'll be using the Euler's notation with the big D. Do note why is not being multiplied in this? It is being derived. So remember that, because you might easily make the mistake of canceling y on both sides. So now let's move 2y to the right hand side of the equation by subtracting it from both sides, creating a homogeneous ordinary fractional differential equation. Let's substitute in the Mittag-Leffler function as mentioned in the beginning. So y equals this function, and that's what we essentially do here. We kind of plug it in. Since our derivation is only with respect to x, we can now pull out non-x terms. So we'll go ahead and pull out anything that doesn't touch or isn't a part of x. We know that earlier the definition for differentiation of the fractional order is the following. We could go ahead and plug that into the equation as well. I know this is really really hard to look at, so bear with me. Number 6. Notice that some terms cancel out and it becomes a lot cleaner. Using the technique we've learned in class regarding the power series, we can raise x to the power of whatever in the first and second term to the same power by adjusting the summation interval. And so we go ahead and do that here. However, gamma function is only defined for numbers that are positive and non-zero. It wouldn't make sense to start our summation from a negative number. So what we'll do is instead just start from 0, and we will adjust the and so we will adjust the rest of the terms accordingly. Now we can pull out like terms and express the equation as a single summation. And since both of these will have to be 0, and this bottom term, this denominator, is constant, we can largely ignore this term because it will resolve to 0 when this term resolves to 0. So we can just focus on this term. And this becomes really easy to solve. This essentially becomes solving a quadratic equation. And from here we can get the values of alpha. And alpha actually becomes a crucial component to our solution, where our final solution is this very familiar equation that we've gone over in this semester, except y1 and y2 is the Mittag-Leffler function. Now this is a very general solution. We can let alpha equals 1/2, and then we get this more specific solution. So what's happening here? What does it mean to derive from the fractional order? If you remember, I told you not to imagine it. Well, now you can imagine it because it's much easier to imagine it while looking at the graphical solution. And as you can see, what it is actually kind of like an intermediate curve between two curves where it maintains the features of the function. In fact, I think the most intuitive notion behind fractional calculus, where we play a video where we differentiate from 1 to 0, and as you can see that this curve kind of transforms to the other curve. So this is very much connected to our curriculum. As you remember, most of the techniques we used to solve that differential equation wasn't anything new. It was essentially the techniques we've been using throughout the semester. We were just using the Mittag-Leffler function and the gamma function. Given the widespread permeating nature of differential equations and that they are everywhere in physics, you can imagine that fractional calculus has also a far-reaching manner. Fractional calculus has gathered some attention quite recently with respect to the overall history of mathematics and is a growing relatively Fractional calculus has gathered some attention quite recently with respect to the overall history of mathematics and is a growing and relatively young field. Some applications include extending the theory of quantum mechanics to fractional quantum mechanics, where we in a sense generalize Schrodinger's wave function. So we take this and then turn it into this. If you are extra attentive, you can see where the fractional calculus kicks in the second equation. Find the Euler notation, find alpha. That's where fractional calculus comes in. It also has applications in acoustics. Fractional calculus serves well in describing the propagation of waves in certain media, proving excellent in modeling. Think of smacking someone in the chest and the waves rippling. It models that very well. Control theory refers to the control of dynamic systems in processes and machines. The aim is to develop a model that controls the processes in the input system in order to bring the system to the desired state, delay, bypass, or margin of error, and to some extent, control its stability. Fractional control theory generalizes the field and aims to provide better solutions and models. In conclusion, fractional calculus allows us to generalize calculus, providing a framework that has far-reaching applications. It is astounding to think that this field may have been born from a rather simple inquiry, growing to a field that has provided bountiful solutions to multiple fields of science and mathematics. Its path to discovery binds different mathematical constructions together into a beautiful, elegant theory, and its rather youthful state gives us a promising vista of the mathematics ahead of us.